To understand what lies beyond the observable universe, you first need to understand precisely what the observable universe is. Not in the sense of memorizing its radius or its age, but in the sense of understanding why that limit exists, why there is a horizon, and what it implies that this horizon exists. The universe began approximately 13.8 billion years ago in a state of extraordinarily high density and temperature that physicists call the Big Bang, though that name is in many ways misleading because it suggests an explosion at a point, and the Big Bang was not that. It was the expansion of space itself from an initial state of high density. There is no center to that expansion, just as there is no center on the surface of a balloon being inflated. Every point in space moved away from every other point, and that movement continues today. During the first 380,000 years approximately, the universe was so hot and so dense that matter and light were intimately coupled. Photons could not travel freely because they constantly collided with charged particles in the primordial plasma. The universe was opaque. In that state, there was nothing to see in any direction even if there had been eyes to see it, because light could not propagate. When the universe cooled enough for electrons and protons to combine to form neutral atoms, approximately 13.4 billion years ago, light was free to travel for the first time. That moment is called recombination, and the light released at that instant is what astronomers detect today as the cosmic microwave background radiation, a radiation that fills the sky uniformly in all directions and is the oldest record we have of the young universe. That cosmic microwave background is the visual limit of the observable universe. Not because there was nothing before it, but because before recombination the universe was opaque and light could not travel. The cosmic microwave background is like the surface of a cloud. You can see the cloud from the outside, but you cannot see through it to see what is behind. What is behind exists, but it is invisible to any instrument based on detecting light. What this means is that the horizon of the observable universe is not an edge of the universe itself. It is an edge of what we can see. The universe may extend far beyond that horizon, and almost certainly does. Measurements of the cosmic microwave background show that the universe is, at the scale of the observable horizon, extraordinarily flat and uniform. In cosmology, the flatness of the universe has a precise technical meaning that describes the curvature of space at a global scale. And a flat universe implies, mathematically, that the universe is either infinite or so large that the curvature is immeasurably small at the scale we can observe. If the universe is flat and extends beyond our observable horizon, it does so in ways we can infer but not directly observe. And those inferences produce images of the universe beyond the horizon that range from the familiar to the radically strange, depending on which cosmological theory we adopt to guide our imagination. The simplest answer, the most conservative one, requiring the fewest additional assumptions, is that beyond the observable horizon there is more of the same universe we see here. More galaxies, more stars, more planets, more empty space, distributed in the same way they are distributed in the universe we observe. Nothing radically different. Just more. Much more. The simplest answer to what lies beyond the observable universe is also the one that takes the greatest effort to absorb, precisely because its scale is so immense that no mind can represent it directly. If the universe extends uniformly beyond our observable horizon, it does so in ways that cosmologists can estimate from measurements of the curvature of space. And those estimates produce numbers that make the observable universe, with its 2 trillion galaxies and its 93 billion light-year diameter, look like a grain of sand. The total universe, if it is flat and if cosmic inflation occurred in the way the most accepted models describe, could be at least 10 to the power of 23 times larger than the observable universe. Written as a number, that factor is a 1 followed by 23 zeros. It is a number that no everyday example can illustrate in a way that intuition can genuinely grasp. It is simply enormous in a way that exhausts any available adjective. Cosmic inflation is the key to this estimate. Inflation is a phase of exponentially accelerated expansion that is believed to have occurred in the first fractions of a second after the Big Bang, before the universe had reached even a tiny fraction of its current size. During inflation, the universe expanded by a factor of at least 10 to the power of 27 in an incomparably brief time. That expansion took regions that were initially in causal contact, that could exchange information with each other, and separated them to distances so large that today they are far beyond the observable horizon. Inflation was proposed in the 1980s by physicist Alan Guth to solve several problems with the standard cosmological model. Before inflation, cosmologists could not explain why the cosmic microwave background is so uniform in all directions. If the universe had simply expanded from the Big Bang at the rate we observe today, opposite regions of the sky would never have been in causal contact and could not have reached the same temperature. Inflation solves this by postulating that all regions of the observable universe were in intimate contact before inflation, and that inflation separated them in incomprehensibly brief times. If inflation occurred, and the observational evidence strongly supports it though it does not prove it with absolute certainty, then the universe beyond our observable horizon is unimaginably large. And in that unimaginably large universe, if the laws of physics are the same everywhere, there would be countless regions like ours. Countless observable universes, each with its own horizon, each as large as ours, distributed in a space that contains them all and is incomparably larger than any of them. This is what cosmologists call the Level 1 multiverse, or the Boltzmann multiverse. It is not the multiverse of science fiction, with parallel universes of different physical laws. It is simply the consequence of a flat and very large universe. In some region of that immense space, the distribution of matter must repeat. If the number of possible configurations of matter is finite, and space is infinite, then every possible configuration repeats infinitely many times, including the exact configuration that constitutes the observable universe from our perspective, including, somewhere incomprehensibly far away, a region of space identical to ours in every detail. This is a conclusion that is difficult to accept intuitively, but that follows mathematically from premises that observational cosmology supports. It is not philosophical speculation. It is a consequence of physics as we understand it today, carried to its logical implications. But the Level 1 multiverse, that unimaginably large universe containing countless copies of the observable universe, is only the first of several possible answers to what lies beyond the horizon. And at each level, the answer becomes stranger, more radical, harder to fit into any intuitive framework. The second level of multiverse arises from eternal inflation. The cosmic inflation we mentioned does not have to have ended at the same time everywhere. The most detailed models of inflation predict that in most of space, inflation continues indefinitely. Only in certain regions, where quantum fluctuations of the field driving inflation cross a certain threshold, does inflation end and a local Big Bang occur that gives rise to a universe like ours. In this model, called eternal inflation, the larger space continues to inflate indefinitely, continuously producing new bubbles in which inflation ends and new universes arise. Each bubble is a separate universe, causally disconnected from the others, with its own Big Bang, its own history, and possibly its own physical constants. In eternal inflation, the number of bubble universes is infinite. Each bubble is inaccessible from the others because the inflation of the space between them separates them faster than any signal could cross that distance. They are separate universes in the deepest sense. Not just far away, but causally disconnected. Nothing that happens in one can affect the others, not even in principle. The physical constants of each bubble universe could be different. The speed of light, Planck's constant, the mass of the electron, the strength of the strong nuclear interaction, All these constants that in our universe have the specific values that allow atoms, stars, planets, and eventually life to exist, could have different values in each bubble universe. In most of those universes, the constants would be incompatible with the existence of complex structures. They would be universes of particles that cannot combine into atoms, or universes that collapse before stars can form, or universes where matter disperses so quickly that it never concentrates into anything interesting. This is the basis of the anthropic principle in cosmology. If countless universes with different physical constants exist, it is not surprising that we are in one with constants that allow the existence of beings who can ask questions. Any being asking why the physical constants have the values they have is, by definition, in a universe where those values are compatible with its existence. Universes with constants incompatible with life exist, but no one is in them to ask the question. This argument is philosophically controversial. Some physicists find it profound and illuminating. Others find it circular and unsatisfying. The debate about the anthropic principle is one of the most intense in the philosophy of physics today, and has no resolution in sight. But the fact that this debate exists, that contemporary physics has reached a point where it seriously considers the existence of countless universes with different physical laws, says something extraordinary about the state of human knowledge at this moment. There is an even more radical level of multiverse that contemporary physics proposes, and it is the hardest to absorb because it requires abandoning one of the most basic intuitions we have about the nature of reality. Quantum mechanics, the theory that describes the behavior of subatomic particles and forms the foundation of virtually all modern physics, has a feature that physicists have debated for almost a century without reaching consensus: measurement. When the state of a quantum system is measured, such as the position of an electron or the spin of a photon, the system transitions from a state of superposition, where multiple possibilities coexist, to a definite state corresponding to the result of the measurement. The process by which this occurs, called the collapse of the wave function, is not satisfactorily explained by the theory itself. It is one of the great open problems of fundamental physics. In 1957, physicist Hugh Everett proposed a radical interpretation of quantum mechanics that resolves the wave function collapse problem in a way that has extraordinary consequences. Everett's many worlds interpretation proposes that the wave function never collapses. Instead, when a measurement or any quantum interaction occurs, the universe branches into all possible branches, one for each possible outcome. In one branch, the electron was detected here. In another branch, it was detected there. Both branches are equally real, but each contains an observer who is only aware of their own result. If the many worlds interpretation is correct, then every quantum decision that has occurred throughout the history of the universe produced a branching. The number of parallel universes that exist in this model is unimaginably large, and it grows every instant with every quantum interaction in every particle of every star of every galaxy. It is a multiverse of a scale that makes the previous levels seem modest. The many worlds of Everett are not separate universes in space. They are branches of the universal wave function that coexist in the same mathematical space. The separation between them is not spatial but in what physicists call Hilbert space, the abstract mathematical space in which the wave function lives. From inside any branch, the others are inaccessible and undetectable. An observer in any branch can only perceive their own history, even though mathematically all other branches exist with equal reality. The many worlds interpretation is taken seriously by many physicists, especially those working in fundamental quantum mechanics and quantum cosmology. But it is not universally accepted, and there are alternatives that also have serious proponents. The question of which interpretation of quantum mechanics is correct is one of the deepest and most debated in all of physics, and will possibly never have an experimental answer because all interpretations make the same predictions for any experiment we can design. What is fascinating, and what makes this level of multiverse so different from the previous ones, is that it arises not from cosmology but from quantum physics. It is not a consequence of inflation or the expansion of the universe. It is a consequence of the most fundamental mathematical structure of the theory that describes the behavior of everything that exists at the microscopic level. If quantum mechanics is correct, and all experimental evidence points to this being so with extraordinary precision, then the question of whether the many worlds are real is in some sense a question about the ontology of the wave function. There is a fourth category of answer to what lies beyond the observable universe that differs in its nature from all the previous ones. It does not propose more space, more bubble universes, or more quantum branches. It proposes something more radical, that physical reality as we know it is, in a precise sense that mathematical physics can articulate, a special case of a broader mathematical structure. Swedish physicist Max Tegmark has proposed what he calls the mathematical universe hypothesis, which holds that every self-aware mathematical structure exists physically. Not that the universe is described by mathematics, which is something all physicists accept, but that the universe is mathematics, that the distinction between mathematical existence and physical existence is illusory. If the mathematical universe hypothesis is correct, then all mathematically possible universes are equally real. Not just universes with different physical constants, but universes with different physical laws, different mathematical structures, different underlying logics. A universe where objects have 11 dimensions. A universe where time has multiple dimensions. A universe where geometry is non-Euclidean at all scales. A universe where interactions between particles follow laws that have no equivalent in any physics we know. This is the most ambitious and most controversial multiverse idea. Tegmark defends it with arguments that many physicists find stimulating, though not all accept them. The most common objection is that a hypothesis that explains everything, that excludes no possible universe, explains nothing in the usual scientific sense, because a scientific theory must make predictions that could be falsified by observation. If all mathematically possible universes exist, there is no prediction the hypothesis can make about what we will observe in ours that is not also consistent with any other possible observation. Tegmark responds that the hypothesis does make a prediction. It predicts that we are typical observers within the set of all mathematically possible structures that contain observers. And that prediction has consequences for the properties we would expect to find in our universe, though those consequences are difficult to calculate precisely. Physicist Lee Smolin has proposed an alternative he calls cosmological natural selection. He suggests that black holes produce new universes with slightly different physical constants, and that universes with more black holes produce more descendant universes. Over time, the distribution of universes would evolve toward those with constants that maximize black hole production. It turns out that the constants that favor the formation of massive stars, which are the ones that produce black holes when they collapse, are also in many cases the constants that favor the formation of complex atoms and eventually life. Smolin's hypothesis produces specific predictions about properties of black holes that can in principle be tested. These hypotheses are not all mutually exclusive. Some are compatible with each other. None is definitively confirmed or definitively refuted by available evidence. They represent the state of the art of serious scientific speculation about the nature of reality at the largest possible scale. There is a question that underlies everything we have explored so far and that deserves to be asked explicitly. If we cannot observe anything beyond the horizon of the observable universe, if all evidence of what is there is by definition beyond our observational reach, in what sense are these hypotheses scientific rather than simply philosophical speculation? It is a legitimate question and physicists debate it seriously. The answer that most cosmologists would accept is that hypotheses about what lies beyond the observable horizon are scientifically valid not because they can be tested directly, but because they are consequences of theories that can be tested. Eternal inflation cannot be observed directly, but cosmic inflation does produce predictions about the cosmic microwave background that can be checked and that have been confirmed with remarkable precision. If inflation is correct, eternal inflation is an almost inevitable consequence of its mechanisms. Similarly, the many worlds of Everett do not produce different predictions from other interpretations of quantum mechanics for any designable experiment, but they follow from taking quantum mechanics seriously as a complete description of reality without adding ad hoc elements like wave function collapse. If quantum mechanics is correct as formulated, the many worlds are a consequence of that correctness. The important distinction is between legitimate extrapolation and unjustified speculation. An extrapolation is legitimate when it is based on well-established theories and when it rigorously follows the consequences of those theories beyond the range where they can be checked directly. An unjustified speculation is one that abandons the framework of established theories without sufficient reason. Hypotheses about what lies beyond the observable universe are in the first category. They are extrapolations of well-established physics, not departures from that physics. What makes them strange is not that they are speculative in the pejorative sense, but that their implications profoundly challenge our intuition about the uniqueness of the reality we inhabit. But there is another answer to the question of whether these hypotheses are scientific, and it is less technical but equally valid. They are scientific in the sense that they are falsifiable in principle though not in practice. If we found evidence that the curvature of space at large scales is positive, that would rule out many models of eternal inflation. If we found evidence that quantum mechanics needs to be modified at a certain scale, that would affect the many worlds. If we found that certain physical constants have values that would be extraordinarily improbable in any set of universes generated by eternal inflation, that would put those models to the test. Science does not require its hypotheses to be testable now. It requires them to be testable in principle and to be coherent consequences of theories that are testable. Multiverse hypotheses satisfy those criteria, though marginally in some cases, and that marginality is precisely what makes their status as science or philosophy debated. What no serious scientist defends today is that these questions are not worth asking or that their answers are irrelevant to understanding the universe. They are the largest questions physics can pose, and the fact that we have answers that are at least coherent and based on real physics is itself an extraordinary achievement of human thought. Something changes when you contemplate these ideas long enough. What changes is not what you know, though you know more. What changes is something harder to name, something related to the scale from which you view yourself and the world you inhabit. We live on a planet orbiting a star on the outer edge of a galaxy of 400 billion stars. That galaxy is one of 2 trillion galaxies in the observable universe. The observable universe is a sphere 93 billion light-years in diameter that is, according to the best available cosmological models, an infinitesimal fraction of a total universe that could be infinite. And that total universe could be one of an infinite number of bubble universes produced by eternal inflation. And each of those universes could be continuously branching into countless quantum branches. From that perspective, the question of whether human life has cosmic importance seems to have an obvious answer. No. We are microscopic organisms on a tiny planet in an ordinary galaxy in an observable universe that is itself an insignificant fraction of all that exists. But that conclusion, though superficially obvious, is actually a conceptual trap. Importance is not measured in cubic meters. Consciousness does not scale with size. And the capacity to ask questions, to contemplate the scale of the universe, to try to understand the nature of reality, that capacity is, as far as we know, extraordinarily rare in the universe. Possibly unique in the observable universe, though probably not in the total universe. Physicist and writer Richard Feynman once described the feeling of contemplating the universe from the perspective of physics as a double wonder. the wonder of what exists and the wonder that we can understand it. That the universe is comprehensible, that its deepest structures are accessible to minds that evolved to hunt and gather on the African savannas a few million years ago, is something no physical theory satisfactorily explains. It is a fact that exists, that seems extraordinarily improbable a priori, and that makes everything else possible. The scale of the multiverse, with all its parallel universes and quantum branches and bubble universes, does not diminish the relevance of consciousness. In a certain sense, it amplifies it. If an infinite number of universes exist, most of them without any observers, then the existence of observers, the existence of beings capable of contemplating the universe and asking questions about it, is something that occurs in a small fraction of that enormous whole. And that rarity, that improbability of consciousness in the context of the multiverse, gives to the experience of being here and thinking about these things a quality that no trivialization can eliminate. Tonight you are doing something that, in the context of everything that exists, is extraordinarily improbable. You are being conscious. You are thinking about the universe. You are asking questions about what lies beyond what you can see. In a multiverse of unimaginable scale, that is no small thing. Let us return for a moment to something more concrete, to the question of how we know what we know about the observable universe, and by extension how we can make inferences about what lies beyond. The most important instrument for studying the deep universe has been, until recently, the Hubble Space Telescope. Launched in 1990, Hubble spent more than 3 decades observing the universe with a clarity no ground-based telescope can match because it sits above the atmosphere that distorts light. Its images of distant galaxies, nebulae, and star clusters have redefined our understanding of the universe in ways that would be difficult to exaggerate. But in December 2021, the James Webb Space Telescope was launched, and since then it has been sending back images of the universe that make Hubble's look blurry by comparison. Webb observes primarily in the infrared, which allows it to see galaxies so distant that their light has been redshifted by the universe's expansion to wavelengths the human eye cannot detect. It has seen galaxies that existed when the universe was only a few 100 million years old, in the first cosmological moments of the history of structures. And what it has found in those primordial galaxies has already produced surprises that are forcing cosmologists to revise their models. Some of the galaxies Webb has observed in the very early universe are surprisingly large and surprisingly mature for their age. Models of galaxy formation predicted that at that epoch the universe would still be in its earliest stages of structuring, with small galaxies gradually merging to form larger structures. What Webb is showing is that some regions of the early universe already had galaxies of size comparable to current galaxies much earlier than the models predicted. This does not refute the models but does put them to the test in ways that will produce new physics. Beyond Webb, astronomers are planning the next generation of telescopes, both space-based and ground-based. The extremely large telescope, under construction in Chile, will have a primary mirror 39 meters in diameter and will be the world's largest optical telescope when operational, expected in the 2030s. The Vera Rubin Observatory, also in Chile, will survey the sky with a depth and frequency unprecedented in astronomy, mapping billions of galaxies and detecting transient events occurring on timescales of days or weeks. The LISA telescope, a space mission from the European Space Agency planned for the 2040s, will detect gravitational waves at frequencies that current ground-based detectors cannot capture, opening a new window on the primordial universe. Each of these new tools will bring us closer to the limit of the observable universe from the inside, revealing more of what exists within our horizon. But none of them will be able to cross that horizon. What lies beyond will remain accessible only through theory and inference, not through direct observation. That fundamental limitation is not a deficiency of technology. It is a consequence of physics. The speed of light is finite. The universe has a finite age. And that establishes a horizon that no telescope can surpass, however powerful. It is the deepest limit that nature imposes on observational knowledge. There is a dimension of this question that is rarely explored in popular science accounts, and that is the temporal dimension. The horizon of the observable universe is not fixed. It changes over time, and it does so in a way that has profound implications for the future of cosmological knowledge. The universe is expanding. Not only that, but the expansion is accelerating. Since 1998, when two teams of astronomers observing distant supernovae independently discovered that the most distant ones were farther away than a decelerating expansion model would predict, we have known that the universe is expanding faster with time. The cause of that acceleration is called dark energy, a name that acknowledges our ignorance. We do not know what it is, only that it produces a repulsive effect that opposes the gravitational attraction of matter. Dark energy represents approximately 68% of all the energy in the universe. Dark matter, which interacts gravitationally but neither emits nor absorbs light, represents another 27%. Ordinary matter, everything we can see, all the stars and galaxies and planets and gas we detect with our instruments, is only 5% of the universe's energy content. We are, in terms of total mass energy, a second-class rarity in a universe dominated by forms of energy we do not understand. The accelerating expansion of the universe has a dramatic consequence for the future of the observable universe. In a universe expanding at constant speed, the observable horizon would grow with time because light from increasingly distant regions would keep reaching us. But in a universe of accelerating expansion, that does not happen. Galaxies that are currently near the edge of the observable universe are receding from us at speeds approaching the speed of light, and with the acceleration, they will eventually recede at superluminal speeds, disappearing from our observable universe forever. Not because they cross any physical barrier, but because the space between us and them expands faster than light can cross that distance. In about 2 trillion years, if dark energy continues with the properties we observe today, most of the galaxies we can currently see will have disappeared beyond our horizon. The Milky Way and the Local Group, the nearby galaxies gravitationally bound together, will remain. But everything else will be gone, invisible, inaccessible, from the observable universe of any civilization that exists then. A civilization arising in the far future, when only local group galaxies are visible, will not have the evidence we have of the Big Bang, of cosmic expansion, of the existence of hundreds of billions of other galaxies. For them, the universe would appear static, finite, composed of only a few galaxies. They would have no way to know what we know, because the evidence would have disappeared beyond the horizon. We would be living in a privileged moment of the history of the universe when we can still see enough to understand the complete story. That is also true in the other direction. Our time window to observe the universe at the scale we observe it today is finite. Every year that passes, some galaxies move slightly farther, slightly closer to the horizon. And astronomers of the far future, if there are any, will have a smaller and evidence-poorer observable universe than ours. We are, in that sense, fortunate to exist now. There is one more extraordinary aspect of this picture that deserves attention before we reach the final chapter of tonight's journey. The cosmic microwave background is not perfectly uniform. It has tiny temperature variations, about 1 part in 100,000, that cosmologists have mapped with extraordinary precision using satellites like COBE, WMAP, and Planck. These variations are not noise. They are information. They are the frozen imprint of quantum fluctuations that occurred during inflation, amplified to cosmic scales by the exponential expansion, and they became the seeds from which all galaxies, all stars, all planets, and all life eventually grew. In a very literal sense, the structure of the universe we see around us, the precise arrangement of galaxies across billions of light years, traces back to quantum fluctuations smaller than any particle during the first fraction of a second. The cosmic web of galaxies and voids that spans the observable universe is a macroscopic image of quantum noise from the inflationary epoch. The same quantum uncertainty that makes electrons behave in ways that defy classical intuition also, when amplified by inflation, gave the universe its large-scale structure. There is something in this connection that stops the mind if you let it. The atoms in your body were forged in the cores of stars and scattered by supernova explosions across the galaxy. The stars that forged them formed in dense regions that concentrated because of quantum fluctuations during inflation. And those quantum fluctuations are, in the many worlds interpretation, the branching points at which the universal wave function split into all possible histories. Every galaxy, every star, every planet, every moment of consciousness in the observable universe has its ultimate origin in quantum events at the beginning of time that also, according to Everett, produced all the other universes in all the other branches. That chain of connection, from the quantum vacuum of the inflationary epoch to the conscious beings asking questions about it tonight, is one of the most remarkable things that physics has revealed. It does not answer every question. It does not explain why anything exists at all. But it shows that everything that exists is connected to everything else at a level of depth that no pre-scientific worldview could have imagined. Tonight you have traveled to the edge of the observable universe and looked beyond. What you found there is not nothing. It is more universe, in quantities that defy any intuition of scale. It is possibly other universes with other histories and other laws. It is possibly infinite branches of the quantum wave function containing every possibility. And it is possibly mathematical structures that exist independently of any particular physical universe. None of those answers is certain. All of them are coherent. And all of them, when you hold them in mind long enough, produce something that knowledge alone cannot produce, a different orientation toward the world. One that includes wonder as a permanent component of experience, that cannot be erased by daily concerns because it is too fundamental to be displaced by the superficial. Tonight you stood at the edge of everything that can be known. You looked beyond. What you saw, though you could not see it directly, is real in the same way that everything physics describes is real. The horizon is there. What lies beyond is there. And you are here, in this moment, in this specific point of an immense whole, conscious of all of it. That is enough for tonight. More than enough. There is a limit. Not a physical boundary, not a wall or a fence or any structure you could touch. But there is a limit. An edge beyond which no telescope, no matter how powerful, can see anything at all. A horizon that physics itself has drawn around us, not arbitrarily but for a reason so deep and so strange that understanding it permanently changes the way you think about space, about time, and about what it means to exist. That limit is called the horizon of the observable universe. And tonight we are going to travel to it, and then we are going to try to look beyond. The observable universe is not all of the universe. It is simply the part of the universe from which light has reached us since the Big Bang. Because the universe is approximately 13.8 billion years old, and because light travels at a finite speed, we can only see objects that are close enough for their light to have reached us since the beginning of time. Everything beyond that horizon exists, in principle, but its light has not yet arrived. It is on its way. It would reach us if we waited long enough. But it has not arrived yet. The radius of the observable universe is approximately 46 billion light-years. Not 13.8 billion, as you might expect if you simply multiplied the speed of light by the age of the universe. The reason the number is larger is that the universe has been expanding throughout that entire time. The light that left the most distant regions of the observable universe 13.8 billion years ago left from a place that was much closer to us at that moment than it is now, because the space between those regions and us has been continuously expanding. When that light departed, that place was at a relatively small distance. By the time that light reached us, that place has receded to 46 billion light-years away. This is one of those cases where physics produces results that completely defy intuition. The observable universe has a diameter of approximately 93 billion light-years, even though the universe is only 13.8 billion years old. It is perfectly consistent with the laws of physics, but it requires accepting that space itself can expand faster than the speed of light without violating any known physical principle. And beyond that horizon of 93 billion light-years in diameter, beyond the limit of what any instrument we could ever build can see, what is there? That question has answers. Not certainties, not established facts, but answers that physics and cosmology propose with varying degrees of confidence and speculation. Some of those answers are extraordinarily humble. Others are extraordinarily ambitious. And almost all of them produce in whoever considers them carefully a sensation that is difficult to name, but has something of vertigo, something of wonder, and something of the strange peace that comes from understanding that the world is incomparably larger than any mind can encompass. Tonight we are going to explore those answers. Not with the urgency of someone searching for data, but with the calm of someone sitting before something immense and letting its scale arrive slowly, in layers, without hurry. Because the questions about what lies beyond the observable universe are also questions about the nature of space, of time, of reality itself. And those questions, if you let them work, have the power to silently transform the way you see yourself in the world. Get comfortable. The universe is enormous. What lies beyond it is larger still. Dark energy is perhaps the deepest mystery in modern cosmology. We know it exists because without it we cannot explain the accelerating expansion of the universe confirmed by supernova observations in 1998. We know it represents approximately 68% of the total energy content of the universe. And we know it produces a large-scale repulsive effect that overcomes the gravitational attraction of matter at the largest cosmic scales. What we do not know is what it is. The simplest explanation, which Einstein proposed and then withdrew thinking it was a mistake, is that dark energy is simply a property of empty space. That the vacuum is not truly empty but has an intrinsic energy, a constant energy density that produces the observed repulsion. This idea, called the cosmological constant, is mathematically elegant and consistent with all available observations. The problem is that when physicists try to calculate the value that this vacuum energy should have from quantum mechanics, they get a number that is between 100 and 120 orders of magnitude larger than the observed value. It is the largest discrepancy between a theoretical prediction and an experimental measurement in the history of physics. That enormous gap is known as the cosmological constant problem, and it is one of the most important open problems in theoretical physics. Resolving it would require a level of understanding of fundamental physics that we do not yet have, and would possibly involve a conceptual revolution comparable to those produced by relativity or quantum mechanics. If dark energy remains constant, the universe will expand forever, with galaxies receding faster and faster until the universe cools and darkens in what cosmologists call heat death. All stars will have burned their fuel, all black holes will have evaporated by Hawking radiation on incomprehensibly long timescales, and the universe will be reduced to a sea of low-energy particles scattered in an infinitely expanding space. If dark energy increases over time, the universe could end in what cosmologists call the Big Rip. In this scenario, expansion accelerates so rapidly that it eventually overcomes the ability of gravity to hold structures together. First, galaxy clusters would be torn apart. Then individual galaxies. Then solar systems. then planets, then atoms, and finally space itself would be torn apart, producing the end of the universe as we know it. We do not know which of these fates awaits us. Current observations are consistent with several possibilities, though heat death in a universe of constant accelerating expansion is the most probable according to data available today. What is certain is that the universe has a fate, and that fate is written in the nature of dark energy that we still do not completely understand. There is a question that standard cosmology does not satisfactorily answer, and that people who think about the universe inevitably ask. What came before the Big Bang? The answer that general relativity gives is that the question makes no sense. Time itself arose with the Big Bang. There was no before because time began with the universe. Asking what came before the Big Bang is like asking what is north of the North Pole. The question presupposes a direction that does not exist in that context. That answer is conceptually impeccable but emotionally unsatisfying. And modern physics offers alternatives that try to give meaning to the question by reformulating it in ways that make it tractable. Roger Penrose's cyclic cosmology proposes that the universe passes through a sequence of eons, each beginning with a Big Bang and ending in heat death. At the moment of heat death, when all massive matter has disappeared and only massless photons remain, the universe acquires a conformal geometry mathematically similar to that of a very small, very hot universe. That moment of heat death can be mathematically connected to the Big Bang of the next aeon. The bouncing universe model proposes that the Big Bang was not an absolute beginning but the bounce of a contracting universe. In loop quantum cosmology, the Big Bang singularity is replaced by a period of maximum finite density, after which the universe bounces and begins to expand. The universe that bounced was itself the result of the contraction of a previous universe, and so on backward in time without an absolute beginning. What all these hypotheses share is that the Big Bang might be a transition, a bounce, a relative beginning within a longer history that has no visible temporal limit. The universe might be eternal toward the past in the same way it could be eternal toward the future, not in the sense that the same universe has always existed, but in the sense that time itself might have no beginning any more than it has an end. One of the most disconcerting aspects of the universe we live in is that its fundamental physical constants appear to be adjusted with extraordinary precision to allow the existence of complex structures. If the gravitational constant were slightly larger, the universe would have collapsed before stars could form. If the strong nuclear force were slightly different, atomic nuclei could not form. If the cosmological constant were only a little larger, the universe would have expanded too fast for gravity to group matter into galaxies. This fine-tuning has a character that seems extraordinarily improbable if the constants were simply random. Physicists have calculated that in the space of possible values of the fundamental constants, the fraction that allows atoms, stars, planets, and life is astronomically small. This argument has been interpreted in very different ways. For some, it is evidence that the universe was designed with the intention of producing life. For physicists working in multiverse cosmology, it is evidence that countless universes with different constants exist, and that we are in one of the few with constants compatible with our existence simply because we could not be in any of the others. The tension between these interpretations is one of the most passionate debates in contemporary physics. The multiverse argument as an explanation for fine-tuning is powerful precisely because it eliminates the need to appeal to any external purpose. If all possible universes exist, ours is not special in any sense requiring additional explanation. But there are physicists who find this explanation unsatisfying. Nobel laureate Steven Weinberg has pointed out that the anthropic argument does not predict which constants we would expect to find, only that we will find constants compatible with our existence. That is too weak as a scientific prediction. A physical theory should tell us why the constants have the specific values they have, not just that they have some value compatible with our existence. The search for a theory that explains the values of the fundamental constants is one of the great programs of theoretical physics. If such a theory existed, it would tell us not only why the constants of our universe have the values they have, but what range of values is possible in principle. And that would give us a much more complete picture of what kinds of universes can exist beyond the observable horizon. In September 2015, the LIGO detectors in the United States captured for the first time a signal physicists had been seeking for decades. Two black holes that had been orbiting each other for millions of years finally merged approximately 1.3 billion light-years away. The event lasted only a fraction of a second, but in that time it released more energy than all the light from all the stars in the observable universe combined, in the form of ripples in the fabric of spacetime that Albert Einstein had predicted exactly 100 years earlier. Those gravitational waves traveled for over 1 billion years through space and arrived on Earth in 2015, where LIGO registered them as an oscillation smaller than 1,000th the diameter of a proton. It is the most precise measurement in the history of science, and it opened a new window to the universe that had not existed before. Before gravitational waves, all astronomy was based on detecting light in its various forms. All those forms of electromagnetic radiation share a fundamental limitation. They cannot penetrate matter that absorbs light. The universe before recombination, the first 380,000 years, is invisible to any telescope based on light because that universe was opaque. Gravitational waves do not have that limitation. They pass through matter with almost no interaction. Gravitational waves from the Big Bang, if they were produced in the way inflation models predict, would have traveled without disturbance from the very first instant of the universe to today. Detecting them would mean accessing information about the universe in its most primitive state, at a time when it was opaque to light but transparent to gravity. That would be the deepest look into the past ever achieved, a window not just to the first galaxies but to the first fraction of a second of existence. Next-generation gravitational wave detectors will be 100 times more sensitive than current ones. With those instruments, astronomers of the near future will be able to listen to the universe in ways we can barely imagine today. And that new way of listening could reveal signatures of what lies beyond the observable horizon, encoded in the primordial gravitational waves that the Big Bang produced. Dark matter represents approximately 27% of the energy content of the universe. It is 5 times more abundant than ordinary matter, the kind that makes up stars, planets, gas, and everything we can see. And yet it neither emits nor absorbs light of any wavelength. It is completely invisible to any telescope. We detect it only through its gravitational effects on ordinary matter. The first evidence for dark matter came from galaxy rotation curves. When astronomers measured the speed at which different parts of a spiral galaxy orbit its center, they found something unexpected. In the solar system, more distant planets orbit more slowly because the sun's gravity weakens with distance. But in spiral galaxies, stars at the outer edges orbit at the same speed as those in the interior, or even faster. That is only possible if there is an enormous amount of invisible mass surrounding the galaxy, extending far beyond what we can see, whose gravity keeps the outer stars in their orbits at otherwise impossible speeds. That invisible mass is dark matter. And it does not just surround individual galaxies. It forms the invisible architecture of the universe at the largest scales. The structure of filaments, walls, and voids that characterizes the distribution of galaxies in the universe, what cosmologists call the cosmic web, is sculpted primarily by dark matter. Galaxies form preferentially at the nodes of that web, where dark matter density is greatest. We do not know what dark matter is in terms of particles. The most popular candidates are weakly interacting massive particles, or WIMPs, hypothetical particles that would interact gravitationally and through the weak nuclear force but not electromagnetically. Extraordinarily sensitive experiments have been designed to detect WIMPs, including detectors buried in deep mines to isolate them from background noise, and so far none has found a definitive signal. In the universe beyond the observable horizon, if dark matter has uniform properties, there would be more of it in the same proportions as in the universe we observe. The cosmic web architecture that characterizes our observable universe would repeat beyond the horizon. The universe beyond the horizon would not be a uniform, smooth space but a structured universe organized in the same way as ours, with its own galaxies, its own groups and clusters, its own voids between the filaments of matter. Stephen Hawking demonstrated in 1974 something no one expected. Black holes are not completely black. They emit thermal radiation as a result of quantum effects at the boundary of the event horizon. As they emit that radiation, black holes slowly lose mass, on incomprehensibly long timescales for stellar mass black holes, but inevitably. The ultimate consequence of Hawking radiation is that all black holes evaporate. And when a black hole evaporates, what was swallowed by it over millions of years must appear in some form in the radiation it emits. Or it must disappear forever, violating the quantum conservation of information. This dilemma, called the black hole information paradox, is one of the deepest open problems in theoretical physics. Its resolution requires reconciling general relativity with quantum mechanics in a way no current theory can fully accomplish. And that reconciliation, when it arrives, could radically change our understanding of space, time, and information at the most fundamental level. If information cannot be destroyed, if everything that falls into a black hole must eventually appear encoded in the radiation it emits, then the universe is a system where no state is permanently lost. Everything that happens leaves a trace, however diffuse and inaccessible that trace may be. The universe remembers. Not in a form any mind can access, but mathematically, in the state of the universal wave function. Holographic quantum gravity, based on Meldesena's conjecture from 1997, proposes that the physics in a space of certain volume is equivalent to the physics on its lower dimensional boundary. A three-dimensional universe can be equivalent, in a precise mathematical sense, to a two-dimensional theory on its surface. If this is true, the distinction between inside and outside, between what is within the observable universe and what is beyond it, may not be as fundamental as it seems. It could be a distinction that arises at the macroscopic level of description but disappears at the fundamental level. Time is perhaps the most mysterious dimension of reality. We experience it as a current flowing inexorably from past to future that cannot be reversed or stopped. But physics has a much more complex relationship with time than everyday experience suggests. The fundamental laws of physics are mostly symmetric in time. The equations describing interactions between particles are valid whether time moves forward or backward. There is nothing in the fundamental equations that distinguishes past from future. And yet we experience time as flowing in one direction. Where does that asymmetry come from? The answer physics offers is related to the second law of thermodynamics and the concept of entropy. Physical systems spontaneously tend toward states of greater disorder, toward greater entropy. A broken glass does not spontaneously reassemble. The direction of time we experience is the direction in which entropy increases. But that leads to another question. Why did the universe start with such low entropy? The Big Bang was a state of extraordinarily low entropy, a state of extraordinary order that has been increasing ever since. If the universe began in a state of maximum entropy, there would be no arrow of time. The fact that there is an arrow of time is a consequence of the Big Bang being a state of very low entropy, and the question of why it was so is one of the deepest questions in theoretical physics. Cosmologist Roger Penrose has argued that the probability of the Big Bang having the low entropy it had is approximately 1 in 10 to the power of 10 to the power of 123. It is the largest number that appears in any serious physical argument, and its enormity makes the fine-tuning of the physical constants seem like a trivial coincidence by comparison. If the universe has a past extending before the Big Bang, if there is a history preceding the history we know, then the initial conditions of the universe we experience could be the result of processes that occurred before. The arrow of time, and the low entropy that makes it possible, could be a consequence of dynamics in the previous aeon, or of the bounce in loop quantum cosmology, or of some selection mechanism in the landscape of eternal inflation. There is a specific way of relating to unanswered questions that is different from ignoring them and different from obsessing over them. It is the way of one who carries them as companions, who lets them surface occasionally, who lets them subtly transform the way they see things, who finds in them an added layer of depth in experiences that would otherwise be more superficial. The question of what lies beyond the observable universe is that kind of question. It does not ask you to change anything in your practical life. It does not ask you to adopt any political position or affiliate with any school of thought. It simply invites you, from time to time, to look at the rock and soil beneath your feet and wonder what story they hold that we have not yet learned to read. To look at the night sky and wonder what other experiments in consciousness might have looked at it from this same planet before we existed. To look at the world with the kind of wonder that comes from knowing that what you see is only a fraction of what exists or has existed or could exist. That way of inhabiting unanswered questions is a form of intellectual and emotional richness that requires no certainty. You do not need to believe that other universes exist to find the question fascinating. You do not need to dismiss it to remain a rigorous skeptic. You only need to be willing to sit with the uncertainty long enough for it to tell you what it has to tell. What it tells you, if you listen, is something about scale. About the difference between the human scale, with its decades and centuries, and the cosmological scale, with its billions of years. About how that difference of scale changes what is possible and what is probable and what is detectable. About how science, which is our best tool for knowing the world, has limits that are real and important and must be recognized for science to remain what it is. What it also tells you is something about the wonder of existing in this specific moment of the universe's history, with the observable universe still full of 2 trillion galaxies, with the cosmic microwave background still detectable, with gravitational waves carrying information from distant black holes. This is a cosmologically privileged moment, and being here, in this moment, asking these questions, is a gift that most moments of the universe will never know. After traveling so far tonight, to the edges of the observable universe and beyond, to bubble universes and quantum many-worlds and mathematical structures that contain them all, there is something worth doing before sleep comes fully. Coming back. Not back in the sense of forgetting what we explored, but back in the sense of bringing that perspective home to where you are. To this planet. To this room. To this moment. The observable universe has a diameter of 93 billion light-years. Inside it are 2 trillion galaxies. One of those galaxies is the Milky Way, with its 400 billion stars. One of those stars is the Sun, with its 8 known planets. One of those planets is Earth, with its single moon, its oceans, its atmosphere, its life. And on that Earth, in this moment, you are here. That path back, from the largest to the smallest, does not diminish the importance of where you end. On the contrary, each step back adds context to what is. Earth is not just a planet. It is the only place in the observable universe where we know with certainty that life exists. The only place where we know with certainty that consciousness exists. The only place where we know with certainty that someone asks these questions. That does not mean Earth is the only place where those things exist. Very probably it is not. But it is the only one we have direct evidence for. And that fact, the singularity of our position as the only known example of consciousness in the observable universe, gives to every moment of conscious experience a quality that the scale of the universe cannot diminish but only amplify. Tonight you contemplated the immense whole from this small point. You used reason to go where perception cannot. You asked what science can answer, and you sat with what it cannot. And now sleep comes, and with it the pause of consciousness that is not the end but the intermission. Tomorrow the universe will still be expanding. The galaxies will still be moving apart. The horizon will still be at 93 billion light years. What lies beyond will still be real and inaccessible. And you will still be part of all of it, part of the only known place in the observable universe where anyone knows the universe exists. The cosmic microwave background is the most ancient light we can observe. It was released approximately 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen for the first time. Before that moment, the universe was a dense, hot plasma through which photons could not travel freely. When the plasma cooled and neutral atoms formed, the universe became transparent, and that ancient light has been traveling freely through space ever since. When we measure the cosmic microwave background today, we are looking at light that has been traveling for approximately 13.8 billion years. The source of that light, the surface of last scattering, is the most distant thing we can see. It is essentially the boundary of the observable universe from the perspective of electromagnetic radiation. Everything we know about what happened before recombination comes not from observing that era directly but from inferring it from the properties of this ancient light. The cosmic microwave background is extraordinarily uniform. The temperature in every direction differs from the average by only about 1 part in 100,000. That uniformity was one of the great puzzles that inflation was designed to solve. How could opposite sides of the sky, regions so far apart that light could never have traveled between them in the age of the universe, be at almost exactly the same temperature? The answer is inflation. Before the exponential expansion, those regions were in causal contact and reached thermal equilibrium, and inflation then pushed them to opposite ends of the observable universe. But the tiny variations in that uniformity, the 1 part in 100,000 temperature fluctuations that satellites like COBE, WMAP, and Planck have mapped with extraordinary precision, are what makes the cosmic microwave background so scientifically rich. Those fluctuations are not noise. They are the fossils of quantum fluctuations during inflation, amplified to cosmic scales by the exponential expansion, and they carry encoded within them information about the very first instant of the universe. The spectrum of those fluctuations, the way the intensity of fluctuations varies with angular scale, tells cosmologists about the geometry of the universe, the content of matter and energy, the nature of inflation, and even whether space might have a non-trivial topology. And it is in the most subtle features of that spectrum that physicists search for traces of what lies beyond the horizon. Certain patterns that would indicate a finite universe, certain correlations that would suggest our bubble collided with another, certain alignments that might hint at a preferred direction in the larger space of eternal inflation. So far, no unambiguous signal of the multiverse has been found in the cosmic microwave background. But the precision of measurements is still improving, and future satellites will map the polarization of this ancient light with a detail that might reveal signatures invisible to current instruments. One of the most persistent misconceptions about the universe is that it exists in a place, that there is some container, some surrounding void in which the universe sits. That image, however natural it feels to minds evolved for navigating three-dimensional space, is deeply wrong. The universe is not in anything. It is everything. There is no outside to the universe in any meaningful spatial sense. When cosmologists say the universe is expanding, they do not mean it is expanding into some pre-existing space. They mean the space that constitutes the universe is itself becoming larger. New space is being created continuously in the sense that the distances between points are growing. The universe is not a balloon expanding in a room. It is more like a balloon whose rubber is space itself, with no room required and no outside edge. This point matters for understanding what lies beyond the observable universe. When we say beyond the horizon, we do not mean in a direction outside some container. We mean simply at distances too great for light to have reached us in the age of the universe. What is beyond the horizon is still part of the same universe, still in the same space, just in a region from which no information has yet arrived. It is not in another dimension or another plane of existence. It is in the same space, just beyond the range of our light cone. The bubble universes of eternal inflation are more complex. In the framework of eternal inflation, they are regions of the same mathematical spacetime, separated by regions of eternally inflating space. They are not in different containers. They are in the same fabric of spacetime, separated by inflation rather than by any physical barrier. The difference between them and the universe beyond our simple horizon is that the separation between bubble universes grows exponentially, faster than any signal could cross, making them permanently causally disconnected. Understanding the universe as not being in a place has a strange consequence for the intuition. If you ask where the Big Bang happened, the answer is everywhere. The Big Bang did not happen at a point in a pre-existing space. It happened everywhere in space simultaneously, because space itself was created in the Big Bang. Every point in the universe is equally the center of the expansion, in the same sense that every point on the surface of an expanding balloon is equally the center of that expansion. And the question of what is at the edge of the universe has no answer, not because we do not know, but because there is no edge. In a flat universe, space extends infinitely, or at least to distances vastly larger than the observable horizon. There is no wall, no boundary, no point at which space stops. The universe, in its full extent, does not end. It simply continues beyond what we can see. Every atom in your body, except for the hydrogen, was forged in the nuclear furnace of a star. The carbon in your cells, the oxygen in your lungs, the iron in your blood, the calcium in your bones, all of it was made by a star that lived and died before the sun was born, and scattered its contents across space in a supernova explosion that seeded the region of the galaxy where eventually our solar system would form. This is not metaphor. It is physical fact. The universe began with only hydrogen, helium, and trace amounts of lithium. Every heavier element, every atom of carbon and nitrogen and oxygen and silicon and iron and gold and uranium, was made by nuclear fusion in stellar interiors or in the explosive deaths of stars. We are literally made of star stuff in the most concrete and material sense possible. And that means that the question of what we are made of is inseparable from the history of the universe. To know what we are made of is to know the history of stellar evolution across billions of years. To know where our atoms came from is to trace a lineage back through supernova explosions, through stellar nurseries, through the primordial nucleosynthesis of the Big Bang, all the way to the first fraction of a second of cosmic time. That chain of physical history connects us directly to what we have been exploring tonight. The quantum fluctuations of inflation became the seeds of the first structures. Those structures collapsed under gravity to form the first stars. Those stars burned through their nuclear fuel, forged the elements, and died in explosions that scattered those elements through space. Later generations of stars formed in clouds enriched with those scattered elements, and around some of those stars, planets formed from the rocky debris, and on at least one of those planets, the chemical complexity built into those elements organized itself into life, and life became complex enough to ask questions about the universe that made it. Every link in that chain is a consequence of the laws of physics and the initial conditions of the Big Bang. Slightly different laws, slightly different initial conditions, and none of it happens. The fine-tuning that allows complex chemistry, that allows stars to burn at the right rate for long enough to allow planets to cool and life to evolve, is written into the chain at every level. The multiverse, if real, is the explanation for why the chain is so precisely tuned. And if the multiverse is real, there are other chains in other universes, most of them broken at some point, a few of them producing their own forms of complexity. But none of those other chains, if they exist, contains you. You are the product of this specific chain, in this specific universe, with these specific physical constants, at this specific moment in cosmic history. That specificity, that particular combination of improbabilities that produced this exact configuration of matter and energy asking questions about the whole, is something the multiverse's existence does not diminish. If anything, knowing how rare it is adds to its significance. We are living through an extraordinary moment in the history of astronomy. The instruments we have now, the James Webb Space Telescope, the gravitational wave detectors, the precision cosmic microwave background satellites, would have seemed like science fiction to astronomers of a generation ago. And the instruments under construction or in planning, the extremely large telescope, the Vera Rubin Observatory, the Einstein Telescope, the LISA space mission, will extend our observational reach in ways we are only beginning to understand. Each new generation of instruments has historically not just answered the questions of the previous generation, but revealed new questions that were not visible before. The Hubble Space Telescope was designed in part to measure the expansion rate of the universe. It did that, but it also discovered that the expansion was accelerating, a result that was completely unexpected and that led to the concept of dark energy. The James Webb was designed to observe the first galaxies. It is doing that, but it is also finding that those galaxies are more mature and more massive than expected, pushing the boundaries of our models of structure formation. What unexpected things will the next generation of instruments reveal? We do not know, by definition. But the pattern of scientific history suggests that the most important discoveries will be the ones we did not plan to make, the anomalies and surprises that force a revision of our assumptions. The universe has consistently turned out to be stranger and richer than our models predicted at any given moment. There is no reason to think that pattern will stop. For the specific question of what lies beyond the observable universe, the most promising near-term direction is the search for primordial gravitational waves in the polarization of the cosmic microwave background. If inflation produced gravitational waves of sufficient intensity, they would imprint a specific pattern called B-mode polarization on the cosmic microwave background. Future missions like LightBird are designed to detect this signal with sufficient precision to test the predictions of specific inflationary models. If B-mode polarization is detected at the predicted level, it would be the strongest confirmation yet of inflation, and by extension the strongest indirect support for the idea that our observable universe is a tiny part of a much larger inflationary space. Beyond that, the detection of signatures of bubble collisions in the cosmic microwave background, though considered highly speculative by most cosmologists, remains a logical target. The specific patterns that such a collision would leave, if it occurred, have been calculated. Whether those patterns exist in the data is a question that better instruments and better analysis techniques could eventually answer definitively. The future of knowledge about what lies beyond the observable universe may also come from unexpected theoretical breakthroughs. A successful theory of quantum gravity, if one is developed, could transform our understanding of the structure of spacetime at the most fundamental level and might reveal aspects of the multiverse that are currently inaccessible to any approach we have. The history of physics suggests that the most profound changes in our picture of the universe have come not from incremental improvements in measurement, but from conceptual revolutions that changed the very framework within which measurements are interpreted. We are, in that sense, always on the eve of the next revolution, though we cannot know from which direction it will come or when it will arrive. There is one more perspective on what lies beyond the observable universe that deserves consideration, and it comes not from the cutting edge of theoretical physics but from the oldest question of astronomy. Why is the night sky dark? In an infinite, eternal, static universe uniformly filled with stars, every line of sight from any point in the universe would eventually end on the surface of a star. The entire sky should blaze as bright as the surface of the sun. And yet the night sky is dark. This contradiction is known as Olbers' paradox, named after the German astronomer who articulated it precisely in 1823, though others had noted it before. The correct resolution to Olbers' paradox is not that the universe is finite in space, though that might also be true. The correct resolution is that the universe has a finite age. Because the universe is only about 13.8 billion years old, light from stars more than a certain distance away has not had time to reach us yet. The most distant stars in the observable universe do not contribute to the brightness of the sky because their light has not arrived. And the universe is not eternal. It had a beginning, and at that beginning stars did not exist. Stars that exist today have not been shining for the infinite time that would be needed to fill the sky with light. The darkness of the night sky is therefore direct observational evidence that the universe has a finite age and that the Big Bang occurred. It is one of the simplest possible observations, accessible to anyone who looks at the sky at night, and yet it contains within it one of the deepest conclusions of modern cosmology. You have been observing cosmological evidence your entire life every time you looked at a dark night sky. You simply may not have known what you were observing. This resolution of Olbers' paradox also illuminates, from another angle, what the horizon of the observable universe means. The horizon is not just a limit of what powerful telescopes can see. It is the limit of what exists in terms of light that has had time to reach us since the Big Bang. Beyond the horizon, the light of stars and galaxies simply has not had time to reach us yet. Those stars exist, shine, and their light is on its way. But it has not arrived. And in that sense, the horizon of the observable universe is a temporal horizon as much as a spatial one. There is something worth pausing on before we reach the final words of tonight's journey. It is easy to focus on the vastness of what we do not know, on the incomprehensible scale of the multiverse, on the depths of uncertainty about what lies beyond the horizon. And that vastness is real and important. But there is something else that deserves equal attention. The extraordinary fact that a species like ours, that evolved to navigate a savanna on a small planet orbiting an ordinary star, has figured out as much as it has about the structure of the cosmos. We did not evolve to understand quantum mechanics or general relativity or inflationary cosmology. Our ancestors had no need to comprehend the cosmic microwave background or gravitational waves or the accelerating expansion of the universe. The minds that developed those concepts, that worked through the mathematics and designed experiments and built the instruments that confirmed the theories, are the same kind of minds that evolved to track animals through grass and recognize faces and remember where water sources are. The fact that those minds can reach from the African savanna to the edge of the observable universe, and then beyond it through inference and mathematics, is one of the most extraordinary things about the universe. It is not given. It was not guaranteed. A universe with different laws might have been fundamentally incomprehensible, might have lacked the regularities that allow mathematics to describe it, might have been too complex for any finite mind to begin to understand. The universe we actually inhabit happens to be one in which the regularities are discoverable, in which the patterns extend from the quantum to the cosmic, in which the same mathematics that describes the orbit of planets also describes the curvature of spacetime and the behavior of particles at the moment of the Big Bang. That comprehensibility is, in the context of the multiverse, not obviously guaranteed. In universes with different physical laws, different mathematical structures, the relationship between mind and world might be different. Consciousness might exist but be unable to comprehend the laws governing it. Or the laws might be comprehensible but produce no consciousness to comprehend them. The fact that we have minds capable of understanding the universe we inhabit is, From the perspective of the multiverse, another form of fine-tuning, another improbable coincidence in the vast space of possible realities. Tonight, in this quiet moment before sleep, that coincidence is present. You are a mind that can contemplate the structure of the cosmos. You live in a universe whose laws are discoverable. You exist at a moment when those laws have been discovered far enough to reveal that the universe is incomparably larger than it appears, that it extends beyond any possible horizon of observation, that it may contain within it endless variety and endless complexity. That is an extraordinary place to be. Whatever else this night is, whatever else tomorrow holds, that fact about this moment is extraordinary. There will come a time, in the incomprehensibly distant future, when the last star in the Milky Way burns out. Not dramatically, not in a supernova, but quietly, the final red dwarf dimming over trillions of years until its nuclear fuel is exhausted and it cools to a dark cinder. By that point, all the galaxies that are not gravitationally bound to ours will have long since crossed the horizon, their light redshifted beyond detection, their very existence unknown to whatever beings might still inhabit the darkness. The universe at that point will be almost unimaginably different from what we observe today. Where now there are 2 trillion galaxies blazing across 93 billion light-years of observable space, there will be only the remnants of the local group, itself eventually merged into a single giant elliptical galaxy slowly cooling and fading. The cosmic microwave background, already at about 3 Kelvin today, will have redshifted to temperatures immeasurably close to absolute zero, essentially indistinguishable from the darkness. Any mind that existed in that era would have no evidence that the universe was ever different. The expansion, the galaxies, the cosmic microwave background, all the evidence that tells us today about the Big Bang and the large-scale structure of the universe would be gone. Those minds would see an apparently static, isolated, dying collection of dark objects in a cold and featureless void. They would have no way of knowing about the universe we live in, no way of reconstructing the cosmological history that we can read so clearly in our telescopes. We live in a cosmologically privileged moment. We exist while the evidence for the history and the scale of the universe is still visible, still accessible, still readable in the ancient light that fills the sky. We have the remarkable good fortune of existing in an era when the cosmos is still young enough, and the observable universe is still large enough, to reveal its own history to those who look carefully. That privilege is worth feeling. Not with pride or self-congratulation, but with something closer to gratitude, the quiet recognition that this moment, in which the universe is readable and the questions it raises are askable, is not guaranteed to any time or any place but happens to be the time and place we occupy. The night sky will be dark again tonight, as it is every night, as it has been for as long as eyes have existed to see it. But the darkness is not empty. It is full of the light of 100 billion galaxies, too distant to see individually but present, their photons crossing the space between us at the only speed the universe allows, carrying with them the story of 13.8 billion years of cosmic history. That light, tonight, is part of the darkness in which you find yourself. The horizon it defines is all around you, and beyond that horizon, whatever is there, is real. One of the most common emotional reactions to learning about the multiverse is a kind of existential vertigo. If there are infinitely many universes, if every possible history plays out somewhere, if our universe is just one of countless others, does anything we do matter? Does our existence have any significance in the face of such incomprehensible vastness? This reaction is understandable, but it rests on a confusion about what makes something matter. Meaning is not a function of uniqueness in an absolute sense. The fact that there are many stars does not make each star unimportant to the planets orbiting it. The fact that there are many people does not make each person's life without significance to those who share it. What matters to us is not what is singular in the cosmic catalog, but what is present in our experience, what is woven into the fabric of our lives and our relationships and our understanding. The multiverse, if it is real, does not diminish any of that. It does not take away the fact that you are here, that you think, that you feel, that you are connected to others who think and feel. It does not change the beauty of a night sky or the depth of a conversation or the weight of a decision or the tenderness of a relationship. All of that remains exactly as real and as present as it was before the multiverse was conceived. What the multiverse does change is the backdrop against which those things occur. It makes the backdrop incomparably larger. It makes our position in the cosmos more humble, in the sense of being a smaller fraction of the whole. But it also makes consciousness, wherever it exists, more precious in a way, more statistically rare against the vastness of all possible realities. In a multiverse of infinite scale, the majority of possible configurations of matter and energy do not produce anything resembling experience. The fraction that does is small, and we are in that fraction. That is not a reason for pride, any more than being born into particular circumstances is. It is simply a description of where we find ourselves. But it is a description that, if you sit with it, produces something that resembles wonder at the specificity of existence, at the improbable particularity of being here, in this universe, at this moment, thinking these thoughts. We have talked about the Big Bang as the beginning of the universe we observe. But there is a deeper question lurking behind that beginning. Why did the universe start in a state of such extraordinarily low entropy? Entropy is a measure of disorder. High entropy states are those where many different microscopic arrangements produce the same macroscopic appearance. Low entropy states are those where only a few microscopic arrangements produce the macroscopic appearance. The second law of thermodynamics says entropy tends to increase over time. Mixed coffee and cream tend not to spontaneously unmix. Broken glasses do not spontaneously reassemble. Heat flows from hot objects to cold ones, not the reverse. The direction of time we experience is determined by the direction of increasing entropy. We remember the past because the past has lower entropy than the present. Causes precede effects because the universe started in a low entropy state and is evolving toward higher entropy. The arrow of time is written into the initial conditions of the cosmos. But why were those initial conditions so extraordinarily ordered? Roger Penrose has calculated that the probability of the Big Bang having the low entropy it had is 1 in 10 to the power of 10 to the power of 123. That number is so large that it has no intuitive representation. It dwarfs any other improbability we discuss in physics. One response to this is that the initial conditions of the universe must be as they are because we are here to observe them. An observer requiring the kind of organized, structured universe we inhabit must, by definition, exist in a low-entropy universe. Universes that started in high-entropy states could not produce observers who remember a past more ordered than the present. But that anthropic response feels incomplete for many physicists. A complete explanation would tell us why the initial conditions were what they were, not just that they must have been compatible with our existence. And that explanation may require understanding the physics of the moment of creation in ways that current physics does not provide. What connects this to the multiverse is the possibility that the initial conditions of our universe were selected by some mechanism, whether it is the dynamics of eternal inflation, the bounce of loop quantum cosmology, or some selection principle in the landscape of string theory. If the initial conditions were selected rather than random, the selection mechanism might naturally favor low-entropy beginnings of the kind we observe. And that would transform the improbability from a mystery to be explained into a consequence of a deeper physical law waiting to be discovered. We have reached, in this journey, something like the end of what physics can say about what lies beyond the observable universe. Not the end of what can be speculated. Not the end of what can be imagined. but the boundary between what follows from established science and what ventures beyond it into territories where the guidance of observation and experiment is no longer available. That boundary is not a failure. It is a feature of any honest intellectual map. The maps that matter are the ones that mark not just what is known, but where the known ends. And this is where the known ends, at the observable horizon, at the boundary of what any instrument based on light can see, at the edge of the causal past of our location in space and time. What is beyond that edge is real. It is not merely possible or hypothetical. The physics that describes our universe, if it is correct, implies that space extends beyond our horizon. And if space extends, it contains something. Most cosmologists believe it contains more of the same universe, more galaxies, more stars, more of the physical processes we observe within our horizon. Some believe it contains regions where the properties of physical reality are different, where the constants that govern chemistry and nuclear physics have different values, where the history of structure formation took different paths. None of these beliefs can currently be tested. That is the honest statement of the situation. The multiverse, in its various forms, is a scientific hypothesis that cannot be confirmed or falsified by any observations we can currently make or envision making. That does not make it wrong. History is full of correct ideas that took generations to confirm. But it does mean that holding those ideas requires a certain comfort with uncertainty, a willingness to reason rigorously about what cannot yet be seen. That comfort with uncertainty, that ability to reason carefully about the unknown, is perhaps the defining intellectual virtue of the scientific enterprise at its best. Not the accumulation of facts, though facts matter. Not the construction of models, though models are essential. But the courage to stand at the edge of what is known and look into the darkness beyond with clear eyes, neither seeing things that are not there nor refusing to acknowledge things that might be. Tonight you stood at that edge. You looked into the darkness. And the darkness, whatever it contains, looked back. Throughout this journey we have explored what physics and cosmology can say about what lies beyond the observable universe. We have seen that the answers science can give are extraordinary, that they lead to images of the universe that far surpass any previous vision, and that they are consistent with the physics we can test in the laboratory and with telescopes. But there are related questions that science cannot answer, not because it is insufficiently advanced, but because they are outside the scope of what science can in principle address. And recognizing that boundary is part of honestly understanding both what we know and what we do not know. Why does anything exist rather than nothing? Not in the sense of why the universe has the properties it has, which is a question physics can in principle address, but in the most radical sense. Why is there reality at all? Why not the null set, the total absence of everything, with no physical laws, no mathematical structures, no possibility of anything? This question has no scientific answer because any scientific answer presupposes the existence of something. Physical laws, mathematical structures, causal principles. Science can describe what there is and how it works. It cannot explain why there is something rather than nothing without using in its explanation something that also requires explanation. Does the universe have a purpose? This question is also outside the reach of science in its purest formulation. Science describes mechanisms, not purposes. It can say how consciousness arose from biological evolution, but it cannot say whether that consciousness has any role in the history of the universe that goes beyond being an epiphenomenon of physical processes. The question of purpose belongs to philosophy and to the traditions of wisdom that humanity has developed throughout its history, and it cannot be answered, confirmed, or refuted by any experiment. Recognizing these limits is not a failure of science. It is a feature of any honest system of knowledge, knowing how far it reaches and where other kinds of understanding begin. Science is extraordinarily powerful within its domain. and its domain is extraordinarily wide. But it is not everything. What science can say, and what we have explored tonight, is sufficient to produce the deepest wonder that the human mind can experience. A universe 93 billion light-years in diameter that is probably an infinitesimal fraction of an incomparably larger whole. Physical constants adjusted with a precision that defies intuition. An expansion that began in the past and will continue toward a future that no living being will see. The possibility that everything that exists is a special case of a broader mathematical reality. Those ideas, contemplated with sufficient patience, produce something that goes beyond knowledge. They produce a different orientation toward the world. One that includes wonder as a permanent component of experience, that cannot be erased by daily concerns because it is too fundamental to be displaced by the superficial. Tonight you stood at the edge of everything that can be known. You looked beyond. What you saw, though you could not see it directly, is real in the same way that everything physics describes is real. The horizon is there. What lies beyond is there. And you are here, in this moment, in this specific point of an immense whole, conscious of all of it. There is a practice that has no name in most languages, but that almost every culture has engaged in throughout human history. Lying down and looking at the night sky for long enough that the scale of it begins to penetrate. Not just seeing the stars as points of light in a dark background, but feeling, in some visceral way, the depth of the space they represent, the distances involved, the age of the light arriving. Most people who have done this describe a version of the same experience. A sense of smallness, first, that is not exactly pleasant but is not exactly unpleasant. Then something else, something harder to name, that comes after the smallness. A kind of liberation, or perspective, or the release of something that felt urgent before looking up and does not feel quite as urgent after. Philosophers have noted this for centuries. The experience of contemplating something vastly larger than yourself produces a characteristic emotional response that Kant called the mathematical sublime. The feeling that arises when the imagination fails to comprehend a scale, but the reason can still grasp it conceptually. The night sky is probably the oldest and most universal source of that experience in human history. What we have done tonight is extend that experience. We have used not just the imagination and the eyes, but the tools of physics and mathematics to push the contemplation further than the visible sky allows. We have gone past the stars we can see to the galaxies beyond, past the galaxies to the cosmic microwave background, past the cosmic microwave background to the inflationary epoch, and then past the inflationary epoch to the hypothetical landscape of eternal inflation and the multiverse. That extended contemplation produces something different from just looking at the night sky, though it includes that. It produces the specific experience of standing at the boundary of what the human mind can access, of reaching the limit of knowledge and looking honestly at what lies on the other side of that limit. And on the other side, not darkness in the sense of emptiness, but darkness in the sense of the unknown, which is not the same thing at all. The unknown is not nothing. It is full of possibilities, some of which physics has given us the tools to characterize, even if not to confirm. And those possibilities, held in mind with appropriate uncertainty and appropriate wonder, are part of what makes this universe, this existence, this moment, something rather than nothing. Carl Sagan wrote that we are a way for the cosmos to know itself. It is a sentence that has been quoted enough times to risk losing its force. But in the context of everything we have explored tonight, it recovers that force with interest. If the multiverse is real, if there are countless universes with different laws and different histories, then consciousness, wherever it exists, is the universe examining itself through a particular window. Not just our universe. Any universe containing observers is, through those observers, achieving a form of self-knowledge. The cosmos becoming aware of itself is not a unique event in our universe. It may be a recurring phenomenon, however rare, wherever the conditions permit. In that picture, the question you are asking right now, what lies beyond the observable universe, is the universe asking itself through you. Not metaphorically. In a very literal physical sense, you are a configuration of matter and energy that was produced by the laws and initial conditions of this universe, and you are now using the information processing capacity of that configuration to model the universe and ask questions about its structure. The universe, through your mind, is reaching back toward its own origins and outward toward its own limits. That is a strange and wonderful thing to be. Not special in the sense of being cosmically privileged or ontologically distinct, but specific in the sense of being this particular expression of the universe's capacity for self-examination, at this particular moment, asking these particular questions. The answers to those questions, as we have seen, remain largely beyond our reach. The multiverse cannot be confirmed by any measurement currently available. What lies beyond the horizon cannot be directly observed. The nature of dark energy and dark matter remains unknown. The resolution of the black hole information paradox is incomplete. The theory of quantum gravity is unfinished. But the questions exist. They are being asked. And the asking of them, the persistence of human curiosity in the face of the incomprehensible, the willingness of minds that evolved for entirely different purposes to turn themselves toward the largest questions their universe can produce, is itself something remarkable. Tonight you were part of that. Your mind reached toward the edge of what is knowable and tried to see beyond. That reaching, that trying, that willingness to sit with uncertainty in the dark, is one of the things that makes consciousness what it is. There is something worth sitting with about the composition of the universe. The matter we can see, the atoms of hydrogen and helium and carbon and iron that make up stars and planets and people, represents about 5% of the total energy content of the universe. The remaining 95% consists of dark matter and dark energy, both of which we have detected only through their gravitational effects and neither of which we understand at the level of fundamental particles or fields. We are, in the most literal sense, made of the minority component of the universe. The stuff we are made of, the stuff we can see and touch and build instruments to detect, is a small fraction of what exists. The dominant components of the universe are things we do not yet understand. Dark matter, at 27%, controls the large-scale structure of the universe. Without dark matter, galaxies would not have formed in the way they did. The cosmic web of filaments and voids that spans the observable universe is a dark matter structure that ordinary matter has simply fallen into. We are living inside a structure built by something we cannot see, shaped by forces whose fundamental nature we do not know. Dark energy, at 68%, controls the ultimate fate of the universe. It is the dominant form of energy in the cosmos today, and it is driving the accelerating expansion that will eventually push all other galaxies beyond our horizon. We live in a universe whose future is determined by an entity we cannot detect except through its effect on distances. What this means, in the context of what lies beyond the observable horizon, is that whatever is there consists mostly of dark matter and dark energy, just as our observable universe does. If the multiverse of eternal inflation exists, then each bubble universe contains its own ratio of ordinary matter, and dark energy, potentially with different values in each bubble depending on how the physical constants settled when inflation ended in that region. The landscape of possible bubble universes is therefore also a landscape of possible compositions, different balances of visible and invisible matter and energy. We understand the 5% well enough to make extraordinarily precise predictions about atomic physics, nuclear physics, chemistry, and biology. We understand the 27% well enough to know it exists and to model its gravitational effects. We understand the 68% well enough to know it is accelerating the expansion. But beyond those observational facts, our understanding runs out quickly. In the face of that ignorance, humility is not just a virtue but an accurate description of our epistemic situation. We have learned an enormous amount about the universe in the past century. We have also discovered that the majority of what the universe contains is something we cannot yet identify. The night sky is full of things we can see, but most of the universe consists of things we cannot. Here is something that physics tells us that seems strange but is completely true. You are at the center of the observable universe. Not in the sense of being privileged or special or occupying some cosmologically significant position. In the sense that the observable universe is defined as the region from which light has had time to reach you. That sphere is centered on you because you are the observer. Every observer in the universe is at the center of their own observable universe. There is no unique center to the universe as a whole, and every point in the universe is equally the center of the observable universe from that perspective. This means that the horizon, that sphere of 93 billion light-years in every direction, is centered exactly where you are. You are enclosed by the boundary of the knowable cosmos. What lies beyond it surrounds you in every direction, incomprehensibly vast, real but inaccessible, part of the same space-time continuum you inhabit but beyond the reach of any signal that has had time to find you. That is a strange and beautiful way to exist. Enclosed by a sphere of everything that can be known from your location, and surrounded by everything that cannot. The boundary is not a wall. It is a temporal limit. What is beyond it is not separated from you by any physical barrier but by the finite speed of light and the finite age of the universe. Given enough time, light from those regions would reach you. But the universe is not old enough yet. The light is on its way. This night, as you lie down to sleep, the universe continues its expansion in every direction from where you lie. The horizon retreats, almost imperceptibly, as the universe ages by the span of your sleep. Photons that were just beyond the horizon when you lay down may have crossed it by morning. New ancient light finally completing its journey to reach the surface of your eye in a world that does not know it is arriving. The cosmos is in motion around you, as it always is, as it always has been. You are at the center of everything that can be known from this particular point in space and time. And beyond the horizon, what lies there continues to be whatever it is, real and unknown and present in the only way the beyond can be present. By implication, by inference, by the mathematics that tells us space does not end at the edge of what we can see. There is a kind of wonder that is not disturbed by knowledge. It is deepened by it. The child who wonders at a star and the astronomer who knows that star is a fusion reactor 93 light-years away undergoing specific nuclear processes are both in contact with something real, but the astronomer's wonder has more layers, more depth, more dimensions. The knowledge does not dissolve the wonder. It gives it more to work with. Tonight we have given wonder more to work with. We have learned that the universe is much larger than the visible sky suggests. That it contains within the observable horizon alone 2 trillion galaxies, each with hundreds of billions of stars. That beyond that horizon, the universe continues, probably much further than the observable region. That the physical constants that govern chemistry and nuclear physics and gravity, the constants that make atoms and stars and planets and life possible, are fine-tuned to a degree that strains credulity if they are simply random. That the expansion of the universe is accelerating under the influence of a form of energy we do not understand. That the structure we see is shaped by a form of matter we cannot directly detect. All of that is real. All of it is supported by evidence. All of it was unknown a century ago, and some of it was unknown a decade ago. The picture of the universe that physics has assembled over the past 100 years is incomparably richer, stranger, and more wonderful than any picture that existed before. And it is almost certainly incomplete in ways we cannot yet anticipate, because every generation of physicists has discovered that reality is stranger than the previous generation imagined. That ongoing strangeness, that persistent capacity of the universe to exceed our expectations and surprise our theories, is one of the most reliable patterns in the history of science. We learn, we build models, we make predictions, and the universe confirms enough of them to tell us we are on the right track, while consistently producing anomalies and surprises that tell us the track is not complete. The cosmic microwave background confirmed inflation. The accelerating expansion surprised everyone. The James Webb Telescope is finding galaxies more mature than expected. The next generation of instruments will find something else that surprises us. That is what the universe is like. It is the kind of reality that keeps being more interesting than we thought. And the question of what lies beyond the observable horizon, which we cannot currently answer, is consistent with that pattern. It is one more case of the universe having more to it than is immediately accessible, more than the current tools can reveal, more than the current theories have anticipated. That should feel exciting rather than frustrating. The unknown is not a wall. It is an invitation. There is one final idea worth sitting with before sleep comes. It is the most abstract and in some ways the most unsettling of everything we have considered. And it is the question of why mathematics works. The physicist Eugene Wigner wrote in 1960 about what he called the unreasonable effectiveness of mathematics in the natural sciences. He was pointing to something that physicists have noted and puzzled over throughout the history of the discipline. The laws of nature can be expressed in mathematical terms of extraordinary precision, and mathematical structures developed with no physical application in mind often turn out, decades later, to describe physical phenomena with uncanny accuracy. Non-Euclidean geometry was developed in the 19th century as pure mathematics, as an exploration of what geometry would look like if one of Euclid's axioms were dropped. It had no physical application when it was developed. Then Einstein showed that it was exactly the mathematics needed to describe the curvature of spacetime in general relativity. Complex numbers, originally conceived as a mathematical trick for handling the square roots of negative numbers, turned out to be the fundamental language of quantum mechanics. Group theory, developed in the 19th century to study abstract symmetries, turned out to describe the symmetries of particle physics with exact precision. Why should this be? Why should the mathematical structures that human minds find interesting or aesthetically compelling turn out to describe physical reality so accurately? There are several possible answers. One is that mathematics is the language of pattern, and the universe consists of patterns, so it is not surprising that mathematics describes it. Another is that we select the mathematical structures we find interesting partly based on their resonance with the physical world we grew up in, so the match is partly a selection effect. A third, which Tegmark's mathematical universe hypothesis makes explicit, is that the universe is a mathematical structure, so of course mathematics describes it perfectly. Whichever answer you find most convincing, the effectiveness of mathematics in physics is one of the deepest connections between human thought and physical reality. It suggests that the mind, in its most abstract mode, when it explores pure mathematics with no concern for applications, is in some sense exploring the structure of reality. The pure mathematician and the cosmologist are both engaged in the same enterprise from different directions, understanding the deep structure of what exists. And that understanding, incomplete as it is, has led us here tonight, to the edge of the observable universe and the question of what lies beyond. The mathematics that grew from human curiosity has given us tools to look 13.8 billion years back in time, to detect ripples in spacetime from black hole mergers a billion light-years away, to infer the existence of dark matter and dark energy from the behavior of visible objects. And it has given us the theoretical frameworks to reason about what might exist beyond the horizon, even if those frameworks cannot be confirmed by observation. The night sky that philosophers and poets have looked at throughout human history is the same sky. But the way of understanding what it is, what it contains, where it leads, has been transformed beyond recognition by the mathematics and physics of the past century. The wonder is the same. The understanding is incomparably deeper. That depth, that accumulated understanding, is one of the things you carry with you into sleep tonight. Not all of it consciously, but all of it present, somewhere, in the network of understanding that tonight's exploration has added to. The horizon remains. What lies beyond it, too? And you, somewhere in the vast dark, thinking about it. There is something particular about the space of time between lying down and falling asleep. The mind is not fully engaged with the demands of the day, but it is not yet given over to the autonomous processes of sleep. It floats, in a way, between the world of intention and the world of dreams, available to thoughts that the daylight hours leave no room for. This space has been called hypnagogia, the threshold state in which the boundary between waking and sleeping becomes permeable, in which the mind generates images and thoughts that have the quality of both. For some people, it is where their most creative ideas arrive. For others, it is where the worries of the day finally find expression. For others still, it is simply a passage, unremarkable, from consciousness to unconsciousness. But it can also be a space for the kind of contemplation that does not belong to any particular task, that has no agenda and no product. The contemplation of the night sky, extended by everything we have explored tonight, is exactly suited to this space. Not because it is drowsy or vague, but because it benefits from the mind's release from urgency, from its willingness in these threshold moments to hold large things without demanding that they resolve. The questions about what lies beyond the observable universe do not resolve tonight. They will not resolve tomorrow, or in any foreseeable time. They will be with us, as a species and as individuals, as long as we remain curious about the cosmos that produced us. And carrying those questions, holding them with appropriate uncertainty and appropriate wonder, is part of what it means to be an intelligent creature in a universe this large. Tonight you carried them. You took them to the edge of what physics can say and looked out from there. And now you carry them into sleep, where they will settle somewhere in the layered structure of memory and understanding that makes you what you are. The universe continues its expansion around you as you sleep. The horizon recedes at the speed of light in every direction. What lies beyond it stays beyond it, real and unknown and present in the only way the unknown can be present, as the darkness beyond the edge of light. Throughout this journey we have explored what physics can say with confidence, what it can say with reasonable extrapolation, and what it can only speculate about. We have tried to be honest about which category each idea falls into. But there is a fourth category that deserves explicit acknowledgement. The things physics cannot say at all, not because it is currently incomplete, but because they are outside its domain. Physics deals with the measurable. It develops quantitative models, makes precise predictions, and tests those predictions against observations. That method is extraordinarily powerful within its scope. But it has a boundary, and outside that boundary are questions that matter enormously to human beings but that cannot be addressed by the methods of physics. The question of why there is something rather than nothing is the most fundamental of these. Physics can explain, in principle, how quantum vacuum fluctuations can produce universes from seemingly empty space. But the quantum vacuum is not nothing. It is a state with properties, governed by mathematical laws, capable of fluctuating. Where do those properties come from? Where do those laws come from? Physics can push the question back by one level but not answer it at the fundamental level. The question of ultimate origin remains beyond its reach. The question of whether existence has meaning is another. Physics describes structures and processes. It does not describe purposes or values. The fact that the universe exists and has the properties it does tells us nothing, by itself, about whether any of this matters. That question is answered, if it is answered, by the choices and relationships and commitments of conscious beings, not by the equations of physics. Physics tells us the stage. It does not tell us what the play is about. The question of what it is like to be conscious is a third. Neuroscience can map the brain processes that accompany conscious experience with increasing precision. It cannot explain why those processes are accompanied by subjective experience at all, why there is something it feels like to be you, rather than all that information processing occurring in the dark with no inner life. That question, what philosophers call the hard problem of consciousness, has resisted every attempt to answer it in terms of physical processes, and the reasons for that resistance run deep. Recognizing these limits is not defeat. It is clarity. The universe contains more than physics can capture, not because physics is incomplete in a way that will eventually be remedied, but because some aspects of reality are not the kind of thing that quantitative measurement can access. That is not a failure of science. It is a description of what science is, and an honest acknowledgement of what lies outside it. Tonight you encountered the boundary of physics in the question of what lies beyond the observable horizon. That boundary is one of the most interesting places physics takes us. The questions that live there are some of the most important questions a mind can ask. And the fact that they cannot be answered does not mean they should not be asked. It means they should be held with appropriate humility, as the honest expression of minds that have gone as far as knowledge can take them and found that the universe extends further still. One of the most profound implications of quantum mechanics, if the many worlds interpretation is correct, is that nothing is ever truly lost. Every event that has ever occurred, every quantum interaction in every particle since the Big Bang, is preserved somewhere in the branches of the universal wave function. The past is not gone. It is contained, in principle, in the mathematical state of the universe, encoded in the pattern of quantum correlations that extends through all of space and time. That does not mean the past is accessible. Most of the information about any specific event is spread across correlations so complex and so diffuse that no practical process could ever recover it. The sensation of loss, of things passing away and being gone, is real in the only sense that matters to beings like us. But at the level of the wave function, nothing passes away. The universe, in the most fundamental sense available to quantum mechanics, is a perfect record of everything that has occurred in it. There is something strangely consoling in that idea, if you let yourself feel it. Every moment that has existed, every configuration of matter and energy that has briefly come together and then dissolved, every flash of consciousness in the history of the universe, is in some sense still present in the quantum state of the cosmos. Not accessible, not recoverable, but not simply gone either. Woven into the fabric of what exists in a way that no ordinary process of decay or forgetting can touch. The universe, in the many worlds interpretation, is the universe as a whole, all branches simultaneously, the complete quantum state that contains all histories. And you are one thread in that state, one path through the branching that makes up all of reality. Your specific path is real, and the fact that other branches also exist does not make your path less real or less specific or less yours. What lies beyond the observable horizon is also contained in that quantum state. The bubble universes of eternal inflation, if they exist, are part of the universal wave function in a sense that physicists are still working to understand precisely. The many worlds branching of the quantum universe we inhabit is connected, mathematically, to the larger structure of the inflationary multiverse. The boundaries between these different conceptions of the multiverse, the level 1 multiverse of a large flat universe, the level 2 multiverse of eternal inflation, the level 3 multiverse of many worlds, are not sharp in the mathematics. They are different aspects of a single framework that describes all of reality. That framework, incomplete as it is is the most comprehensive picture of reality that the human mind has yet produced. Tonight you sat within it, at the specific location in space and time that is yours, and reached outward toward its edges. That reaching is part of what the framework is, part of what makes consciousness the phenomenon it is, the universe using one of its localized configurations to try to understand the whole. We have explored tonight the physics of the horizon, the mathematics of the multiverse, the philosophy of what can and cannot be known. We have traveled through the history of the universe from the Big Bang to the far future, and we have tried to look beyond every boundary that presents itself. At each boundary, we found not a wall but a gradient, the known shading into the inferred shading into the speculative shading into the honestly unknown. No sharp line, no final answer, but a continuous recession of the knowable into the depths of the unknown. That recession is not a failure. It is the shape of any honest inquiry into a universe that is richer than any finite mind can encompass. The horizon of the observable universe is one expression of that richness. The questions that arise at that horizon are another. The fact that those questions cannot be answered is another still. What we have done tonight is not arrive at answers. We have clarified the questions. We have understood better what the questions are, why they are difficult, what kinds of answers are possible in principle and which are not. We have traveled to the boundary of physics and looked at what lies on the other side of that boundary with as clear eyes as the tools we have allow. That is enough. That is actually a great deal. The clarification of questions is underrated as an intellectual achievement. We started tonight not knowing precisely why the horizon of the observable universe exists. We do now. We started not knowing what physics says about what might lie beyond it. We have explored that now. We started not knowing the different levels of multiverse that physics proposes. We have mapped those levels now. The universe remains as vast as it was before this journey. The unknown remains as deep. But the map of the known has been extended by this exploration, and the relationship between the known and the unknown has been made more precise. That is the whole project of science. Not to eliminate the unknown, but to make the boundary between the known and the unknown sharper, more honest, more precise. Tonight that project extended to the edge of the observable universe. Tomorrow it continues. 13.8 billion years. Let us try to feel that number rather than just state it. A human lifetime, generously, is 100 years. 13.8 billion years is 138 million human lifetimes. If you stretched a single lifetime across a football field, and then stretched 13.8 billion of them end to end, you would need a line almost 3 million kilometers long, 8 times the distance from the Earth to the Moon. That is the age of the universe. The light reaching your eyes from the most distant galaxies we can observe left its source when the universe was not yet 1 billion years old, when the first stars were barely beginning to illuminate the cosmic dark ages. Everything that has happened in the history of human civilization, all of recorded history from the first writing in Mesopotamia to this present moment, occupies less than the final 0.005% of that 13.8 billion years. In that context, the question of what came before the Big Bang, of what lies beyond the observable horizon, of whether the universe is one of many, does not seem like idle intellectual speculation. It seems like the natural extension of the wonder that anyone should feel when they grasp, even imperfectly, the scale of the universe they inhabit. The universe is not a backdrop. It is not a stage on which human history is performed. It is a thing in itself, immense and ancient and complex and mostly unknown, of which human history is an almost undetectably brief footnote. And yet that footnote is the only place, as far as we know, where the universe has become aware of itself, where matter has organized into structures that ask questions about the whole. The paradox of our position in the cosmos is that we are almost nothing in quantitative terms and almost everything in experiential terms. By any measure of size or age or energy, we are negligible. By any measure of the capacity to ask questions and to understand, we are remarkable. Both of those things are simultaneously true, and holding them together without collapsing into either grandiosity or nihilism is part of what it means to think honestly about our place in the universe. There is a way of relating to unanswered questions that treats them not as problems to be solved, but as practices to be maintained. Questions about the ultimate nature of reality, about what lies beyond any horizon, about why anything exists at all, may never have answers. Or they may have answers that are currently beyond our reach. In either case, holding them as practices rather than problems changes the relationship. A practice is something you return to regularly, something that deepens not by advancing toward a conclusion but by being held more fully, understood more richly, felt more completely over time. The practice of contemplating the night sky is not advanced by arriving at a destination. It is deepened by looking more carefully, more honestly, more repeatedly. The practice of asking what lies beyond the observable universe is not advanced by answering the question. It is deepened by asking it more precisely, understanding better what kinds of answers are possible, sitting with the uncertainty more completely. This may sound like a consolation prize for the inability to answer the question. It is not. It is a recognition that some questions are not problems to be eliminated but orientations to be cultivated. The question of what the universe ultimately is, what lies at the deepest level of physical reality, what consciousness is and how it relates to matter, these are questions that every generation of thoughtful people has asked and that every generation has found to be inexhaustible. They do not diminish with engagement. They deepen. Tonight you engaged with some of those questions. You did not solve them. You could not have. But you have, if this journey landed in the way such journeys can, a slightly different relationship with the night sky than you had before. A slightly different sense of what is out there, what is known and unknown, what the horizon means and what lies on the other side of it. That is not a small thing. That is the thing. The sleep coming now is a smaller horizon than the edge of the observable universe, but a horizon nonetheless. Beyond it is the rest of the night, the morning, the continuation of whatever life you are living. On this side of it is the person who has spent this time thinking about the largest things there are. Both sides of that horizon are real. Both matter. And the mind that crosses it tonight carries something it did not have before. There is a tradition in certain forms of meditation and contemplative practice of cultivating a felt sense of connection with something larger than the self. Not a belief exactly, but a felt quality of presence, of being part of something that extends beyond the boundaries of individual existence. The universe, known to us through physics in the way we have explored it tonight, is a candidate for that something larger. Not in a supernatural sense. Not as a being with intentions or awareness. But as the actual context of existence, the actual fabric within which consciousness arises, the actual history that produced everything that is. The atoms in your body were formed in the Big Bang or in the cores of stars. The light reaching your eyes has traveled from sources across billions of years of cosmic history. The ground beneath you has been part of the Earth for 4.5 billion years, itself formed from the debris of earlier stellar generations. The air you breathe contains oxygen produced by photosynthesis over billions of years of biological evolution. You are not separate from the universe. You are a configuration of the universe, temporarily organized in a way that allows self-awareness. That felt sense of being part of the larger whole, of being a specific expression of what the universe does when it has enough time and the right conditions, is available to anyone who thinks carefully about what the universe is and how they relate to it. It does not require any belief beyond what physics establishes. It requires only a willingness to feel, rather than just know, the implications of what is established. Tonight you have spent time with the universe at its largest scales, with the 14 billion years of cosmic history, with the 2 trillion galaxies of the observable universe, with the physics of what lies beyond the observable horizon, with the improbability of consciousness existing anywhere in such a vast and mostly dark and empty cosmos. That time, if it produced anything, produced a slightly more vivid sense of what you are part of, a slightly clearer picture of the context in which your life is occurring, and a slightly more settled sense, perhaps, of the proportion between the things that seem urgent and the things that are actually large. The universe is with you now, as it always has been, as it always will be. The horizon is all around you. What lies beyond is real. And you, this specific and improbable configuration of matter and energy that can ask questions about all of this, are here. That is the last thing to carry into sleep. There is an old philosophical distinction between what can be said and what can only be shown. Some truths can be stated in propositions and verified against evidence. Others can only be pointed toward, and whether you apprehend them depends on whether you are already oriented in the right direction to receive what the pointing indicates. The physics of the observable universe can be said. The equations of general relativity and quantum mechanics can be written down. The measurements of the cosmic microwave background can be described precisely. The evidence for dark matter and dark energy can be presented. All of that belongs to the domain of what can be said. What lies beyond the observable horizon is somewhere between what can be said and what can only be pointed toward. The multiverse hypotheses are, as we have seen, legitimate extrapolations of well-established physics. They can be expressed mathematically, and their implications can be worked out. In that sense, they belong to the domain of what can be said, even if what they say cannot be verified. But the quality of the unknown itself, the texture of the boundary between the knowable and the unknowable, the felt sense of standing at the edge of what any mind in our position can access and looking into the darkness beyond that edge, that is something that can only be shown. And what tonight has tried to do is show it, by following the physics as far as it goes and then honestly acknowledging where it stops. You are at that edge now, or as close to it as the journey of tonight has brought you. The edge is not a wall. It is a horizon, and every horizon, approached closely enough, turns out to contain another horizon beyond it. But for this night, for this journey, this is the edge we reached. Beyond it, what physics predicts but cannot confirm? What reason infers but observation cannot reach? What exists, in whatever sense the beyond the horizon exists, waiting, as it always has, for whatever comes next? The universe is patient. It has been here for 13.8 billion years. The questions will still be there tomorrow. Before sleep takes you completely, one small thought to carry into the dark. The light from the most distant galaxies we can observe has been traveling for over 13 billion years to reach you. It left its source when the universe was young, when the first stars were just beginning to blaze through the cosmic dark ages, and it has crossed billions of light years of expanding space, redshifting from visible light into infrared and then into radio waves as the expansion stretched its wavelengths, and it arrived here, at this planet, at this atmosphere, at these instruments and these eyes. That light does not know it has arrived. It has no destination. It travels because that is what light does, at the only speed the universe allows, in a straight line through curved spacetime, until it is absorbed by something. Tonight, in the instruments of astronomers, and in the light of distant stars visible to the naked eye, some of that ancient light has been absorbed by matter configured into consciousness. And that consciousness is asking about the universe that produced it. There is something in that image that does not need to be explained or analyzed or resolved. It can simply be held, here at the edge of sleep, as a description of what is happening. Ancient light arriving at questioning minds, the universe examining itself through the only means it has found for doing so, in the brief and improbable window of time when such questioning is possible. You are part of that. You have always been part of that, whether you knew it or not. Tonight you knew it a little more. Right now, as you read this, the observable universe is approximately 93 billion light-years in diameter. It has been growing, by the speed of light in every direction, since the Big Bang. It will continue to grow. But the galaxies at its edge are moving away from us faster than the growth of the horizon, so the number of galaxies we can observe is actually shrinking over cosmic time, not growing. This means we live in a particularly rich observational moment. More of the universe is visible to us today than will be visible to any observer in the far future. In 1 trillion years, only the local group will remain within the observable universe of any civilization that exists then. The evidence we have of the Big Bang, of cosmic expansion, of the cosmic microwave background, of the large-scale structure of 2 trillion galaxies, all of it will be gone, beyond an event horizon that no future observer can cross. We are the witnesses of the universe at its fullest accessible extent. No future civilization, however advanced, will be able to see what we can see. The evidence for the history of the cosmos that is available to us today is a gift of cosmic timing that will not be repeated. That is not a reason to feel burdened. It is a reason to feel, if anything, a quiet gratitude for existing in this particular window, for having instruments that can read the ancient light, for having minds that can ask what it means and where it came from and what lies beyond the edge of all that can be seen. The universe tonight is doing what it always does, expanding, creating distance, letting galaxies drift beyond horizons, letting stars burn and die and scatter their elements, letting consciousness, in the places where it has arisen, ask its questions in the dark. You are one of those places. Tonight you asked. If this journey kept you company tonight, subscribe to the channel.